Lewis structures are a way of representing an atom, compound or ion. These structures show how the valence electrons are arranged, and because they use dots to represent the electrons, they're sometimes also called electron dot structures. There are a series of steps involved in drawing Lewis structures, and we're going to walk through these now. Let's use a water molecule as an example. So step 1 is add up the total number of valence electrons in the molecule or ion. We know that water is H2O, which means that it consists of 2 hydrogen atoms and 1 oxygen atom bonded together. To add up the number of valence electrons in the molecule, we can simply look at which groups hydrogen and oxygen belong to on the periodic table. Remember that group number equals the number of valence electrons. So hydrogen's in group 1, and there are 2 of them. So this corresponds to 2 lots of 1 valence electron. And oxygen's in group 6, which means it has 6 valence electrons. And 2 lots of 1 plus 1 lot of 6 equals 8. So there are 8 valence electrons in a water molecule. Step 2 is write the symbol for each atom in the molecule or ion and put the odd one in the middle, if there is an odd one. So in this case we have 2 hydrogen atoms and the odd atom is an oxygen atom. So we place this in the middle between the 2 hydrogen atoms. Step 3 is spread the valence electrons around in pairs so that every atom has access to 8 electrons, except hydrogen, which only needs 2 electrons. Why 8 electrons? Because of the octet rule, which states that atoms want to form a stable outer shell of 8 valence electrons. In Lewis structures, these electrons are represented by dots. So we know that our 2 hydrogen atoms are going to be happy with 2 electrons. So we draw a pair of 2 electrons next to each hydrogen atom. We need to draw the electrons where they can be shared by both hydrogen and oxygen, so that means they go in between the symbols. When we draw these 2 pairs, that gives us 4 electrons. We now have 4 valence electrons left, and these go next to oxygen. We can now see that both of the hydrogen atoms have access to 2 electrons, which is what they want, so both are happy atoms. And the oxygen in the middle has access to 8 electrons. That makes the oxygen atom happy too. The last step, step 4, is to draw any bonds between atoms. We can see that 2 pairs of electrons are being shared between the oxygen and the hydrogen atoms. This means that a single covalent bond exists between each hydrogen atom and the oxygen atom. 1 pair of electrons equals 1 bond, and we represent these bonds with a single line instead of the 2 dots. If each bond consisted of 2 pairs of electrons, this would be a double bond, and we draw a double line. If the bonds consisted of 3 pairs of electrons, they'd be triple bonds, and we draw a triple line. But water is nice and simple. It has 2 single bonds, each consisting of 1 pair of shared electrons. The electron pairs that aren't part of the bond are called lone pairs. So that's how we draw a water molecule using Lewis structures. Let's try another example, the stinky gas methane, which is CH4. Step 1 is to add up the total number of valence electrons. Methane has 1 carbon atom, and because carbon's in group 4 of the periodic table, it has 4 valence electrons. And methane also has 4 hydrogen atoms. Hydrogen's in group 1 of the periodic table, so there's 1 valence electron in each atom. And 1 lot of 4 plus 4 lots of 1 equals 8. So there are 8 valence electrons in a methane molecule. This is just a coincidence, by the way. Not all molecules have 8 valence electrons. Step 2 is to write the symbol for each atom in the molecule and put the odd one in the middle. In this case, the odd atom is carbon, so it goes in the middle and is surrounded by 4 hydrogens. Step 3 is to spread the valence electrons around in pairs so that every atom, except hydrogen, has access to 8 electrons. We know that each hydrogen atom only wants access to 2 electrons, so we can draw these between each hydrogen atom and the carbon atom. That gives us 8 electrons in our Lewis structure, which is all the electrons we have. But that's okay, because it means that each hydrogen atom has access to 2 electrons, which is exactly what they want. And the carbon atom, which shares those electrons, has access to 2, 4, 6, 8, which is exactly what the carbon atom wants. So everyone's happy. Now for the last step, step 4, which is to draw any bonds between atoms. Our final Lewis structure therefore has 4 single bonds, with each bond consisting of 1 pair of shared electrons. Let's do one more example, a slightly trickier one this time, carbon dioxide. So, step 1, add up the total number of valence electrons present. We have 1 carbon plus 2 oxygen atoms. Carbon's in group 4, so it has 4 valence electrons. Oxygen's in group 6, so it has 6 valence electrons. And 4 plus 12 equals 16. So in this case, we have 16 valence electrons to play with. Step 2 is to write the symbols for each atom with the odd atom in the middle. Carbon's the odd one out, so it goes in the middle with 1 oxygen atom on each side. Step 3 is to spread the valence electrons around in pairs so that every atom except hydrogen has access to 8 electrons. In this example, there's no hydrogen present, so according to the octet rule, every atom wants 8 electrons. Let's try drawing these electrons from left to right. 1, 2, 3, 4, 5, 6, 7, 8 around oxygen, 9, 10, 11, 12, 13, 14 around carbon, and 15, 16 around the second oxygen. And we've run out of electrons. Remember, we only have 16 valence electrons to play with. So this configuration won't work because not all the atoms have access to 8 electrons. Perhaps we should be considering making double bonds instead of single bonds. And as we know, double bonds consist of 2 pairs of electrons instead of 1 pair. So let's try removing 1 pair from around oxygen and sharing it between oxygen and carbon. We can now see that the oxygen atom still has access to 8 electrons. However, it's now sharing 4 electrons, or 2 pairs of electrons, with carbon. However, now the carbon has access to 10 electrons, which is too many. So let's remove this pair and share it between the carbon and the second oxygen. And let's take this other pair away from the carbon and give it to oxygen. This seems to work out well. Both oxygen atoms have access to 8 electrons, and the carbon atom also has access to 8 electrons, which it shares with the oxygen atoms. And there's a total of 16 electrons spread around the structure. Perfect. Now for step 4, to draw the bonds. The carbon atom is sharing 4 electrons, or 2 pairs of electrons, with each of the oxygen atoms. This gives us 2 double bonds. This molecule also contains some lone pairs, 2 lone pairs on each oxygen. And there is our completed Lewis structure. However, carbon dioxide is an interesting example because there are actually a few ways that you could distribute the electrons. We could, for example, draw 6 bonding electrons and 1 lone pair around the first oxygen atom, and 1 bonding pair with 3 lone pairs around the second oxygen atom. In this configuration, the first oxygen atom has access to 8 electrons, and the second oxygen atom has access to 8 electrons. The carbon atom in the middle also has access to 8 electrons, and there are 16 electrons altogether. So to redraw this, we would draw a lone pair, a triple bond, a single bond, and 3 lone pairs. Or we could have drawn it in the opposite way, with the triple bond on the other side. Now, because each of these structures satisfies the octet rule and uses 16 electrons, all of them are possible. So if I had a container of carbon dioxide, you'd find the molecules in any one of those 3 arrangements. The terms for these different forms of the same molecule is resonance structures. Not every molecule has resonance structures, but many do. And drawing any one of the resonance structures for a molecule will be correct.